With Doubtnut, get instant video solutions to all your maths, physics, chemistry, and biology doubts. Just click the image of the question, crop the question, and get instant video solution. Download Doubtnut app today.
Actually, it should be Stefan-Boltzmann law. And then we have to define emissivity of a material, which is a property of material. Then we have to derive Newton's law of cooling. And finally, we have to plot a graph between temperature and the time. So what is Stefan-Boltzmann law? Stefans and Boltzmann, these were two scientists. Boltzmann law, and they give the law for a black body, and according to them, for a perfectly black body, black body is a body which absorbs all the radiations. The intensity of radiation is directly proportional to fourth power of the temperature. Intensity of radiation is directly proportional to T raised to power 4, or you can write it fourth power of the temperature. Okay. And for a black body, we can note down for a black body, all the radiations are absorbed by the body, and emission is equal to absorption. And mathematical form of law we can write intensity of radiation. If intensity of radiation is Q, then Q will be directly proportional to T raised to power 4. If A is the area and T is the time, and T is the time because heat transfer will take some time, then we can write it Q upon A into T. This is amount of energy radiated per unit area per unit time. That will be also proportional to T raised to power 4. And re-engineering this equation, we will get Q is equal to some constant A into T raised to power 4 into time, or we can write it in rate. Rate is the Q divided by T. Rate of heat transfer, that is Q by T, will be equal to, and this constant K in heat radiation, this constant is known as sigma, and sigma was Stefan-Boltzmann constant. It is Stefan-Boltzmann constant, and value of the sigma is 5.67 into 10 raised to power minus 8, and the unit can be determined through the formula. Unit will become watt per meter square Kelvin to the power 4. So rate of heat transfer, heat amount of heat radiation will be sigma A T raised to power 4. We will derive the Newton's law of cooling through this formula in Boltzmann law. Now next part in this question is define the emissivity of a material. So what is emissivity? Emissivity of a material. Actually, it is a property. Emissivity. Emissivity is defined as the ratio of the energy radiated, the energy which is radiated in EMW, electromagnetic waves, radiated from a material surface, from a materials surface to that radiated from a perfect emitter, to that radiator, we can write it radiated from a perfect emitter, and perfect emitter is a black body, and perfect emitter is a black body. We can define it like a ratio of energy radiated from any material surface to the radiated energy from a black body. Okay, so if epsilon is the symbol for emissivity, then it should be ratio of energy radiated. If energy radiated is Q, you can take it Q from any material divided by energy radiated from a black body. This is the concept of emissivity. And our question is what is emissivity of a material? If you want to write it in terms of emissivity of material, we can write it emissivity of material divided by emissivity of a black body. Then emissivity of a material will become emissivity into emissivity of a black body. And this emissivity is defined for, this is defined for the same temperature and wavelength and I want to add one more point. The emissivity of surface depends not only on the material but also on the nature of the surface. Now next part of the question is derive Newton's law of cooling and plot the graph between temperature and the time. Now Newton's law of cooling. Newton's law of cooling. It means this law is for amount of heat radiated. It says the rate of loss of heat. If there is a loss of heat, there will be a process known as cooling of a liquid is directly proportional to the difference of temperature of the liquid and the surrounding. Temperature of the liquid and the surrounding. Let T is the temperature of the liquid and T naught is the temperature for the surrounding. And mathematical form of the law, you will find T naught is the temperature of the surrounding or atmosphere. And this temperature difference is very small. T minus T naught is very small. We can write T is approximately equal to T naught. Then amount of loss of heat will be directly proportional to T minus T naught from the statement of the law, and both are temperature in Kelvin. Right? But this T is slightly greater than T naught. These are approximately equal, but there will be a slight difference. That's why there will be a loss of heat. Now, according to Stefan law, from Stefan-Boltzmann law, we can also write Stefan-Boltzmann law. the amount of heat energy lost per second per unit time and per unit area of the body was Q divided by A by T is equal to sigma T raised to power 4. But there is a temperature difference, and for temperature difference there will be a heat transfer. Heat transfer will be AT sigma T is the temperature of the liquid, so it will be T raised to power 4 minus T naught raised to power 4. We can write Q is equal to sigma A into T raised to power 4 minus surrounding temperature to the power 4. Here sigma is a constant, and Q, if we rearrange this equation, Q can be written as sigma A into T. It will be T square minus T naught square. I'm applying here A power 4 minus B power 4 will be T square plus T naught square. This T is approximately T naught, and T square minus T naught may be written as a T minus T naught. I'm applying the formula for A square minus B square into T plus T naught. So putting all the values in equation, you will get Q is equal to sigma AT T minus T naught and T naught plus T naught square plus T naught square. We cannot write here 0 because there is a slight difference, and finally we will get sigma AT T minus T naught, and it will be 4 T naught to power 3, right? So Q, that is the amount of heat, radiation or loss of heat, will become a constant value. This is a constant value. I'm writing the value of K into T minus T naught, and this constant is sigma is a constant, A is the constant, T for for 3 seconds or 4 seconds there will be a loss of heat into 4 times of T naught to the power 3. This is a constant, so we can write it Q will be directly proportional to T minus T naught, and this is the statement of Newton's law of cooling. Okay, and I proved this law through Stefan-Boltzmann law. Thank you for watching the session.
For class 6 to 12, IIT JEE and NEET level. Trusted by more than 5 crore students. Download Doubtnut app today.